Hello there, and welcome to Space Historians. I'm so glad you found your way here tonight. Before we begin, take a moment to settle in wherever you are. Let your body sink into comfort, releasing whatever tensions the day has left behind. There's nowhere you need to be, nothing you need to accomplish, just gentle exploration ahead. Where in the world are you right now? A quiet room where you can finally let your mind rest. A peaceful space where the day's noise has faded. Wherever you are, you're exactly where you need to be. Tonight we're going to explore one of reality's deepest questions. How many dimensions do we really live in? We'll discover that the three spatial dimensions we experience might be just a fraction of reality's true structure, that hidden dimensions could be curled up at every point in space, and that extra dimensions might explain gravity's weakness and unify all forces of nature. The answer might be far stranger than we imagine. But don't worry, this isn't going to be an overwhelming journey through impenetrable mathematics or a dizzying plunge into abstract geometry. Instead, we'll move slowly and thoughtfully through these concepts, building understanding piece by piece, finding clarity in what seems impossibly complex. By the end, I think you'll have a richer appreciation not just for dimensions themselves, but for how they shape everything we experience. If you enjoy these calm explorations of reality's hidden structures and fundamental questions, a like and subscribe really helps reach others seeking the same peaceful way to end their day. And to those already subscribed, thank you for being part of this community of curious minds. So settle in now. Let your shoulders drop, releasing tension you didn't know you were carrying. Take a slow, deep breath in, feeling your lungs expand and release it gently. Feel yourself sinking deeper into comfort with each exhale. And let's begin our slow drift through dimensions, exploring the familiar three we navigate daily and the hidden extra dimensions that might exist at every point in space. There's nowhere you need to be, no boundaries you must cross. Just listen and let the mysteries of dimensionality unfold like space itself, extending in directions we cannot see. To understand whether extra dimensions exist, we must first appreciate the three spatial dimensions we experience every day and take for granted. Dimensions are independent directions in which you can move. They're the degrees of freedom that define spatial location and extent. The first dimension is a line. It has length but no width or height. Movement is restricted to forward and backward along a single axis. A one-dimensional being could only move along this line, unable to escape it or perceive anything beyond. The second dimension adds width. A plane has length and width but no height. Movement can occur in two perpendicular directions. A two-dimensional being living in a plane could move forward, backward and left-right, but couldn't conceive of up or down. The third dimension adds height. Space has length, width, and height. Three mutually perpendicular axes define three-dimensional geometry. This is the space we inhabit. We move through three independent spatial directions: forward-backward, left-right, and up-down. These three dimensions seem complete. We can reach any point in space by specifying three coordinates: x, y, and z. Our intuition, shaped by evolution in three-dimensional space, finds three dimensions natural and sufficient, but mathematics allows for more. There's nothing preventing 4, 5, or any number of spatial dimensions mathematically. Higher dimensional spaces are well defined geometrically. We can calculate distances, angles, and volumes in any number of dimensions. The question is whether these mathematical possibilities correspond to physical reality. Do extra spatial dimensions beyond the familiar three actually exist in our universe? Or are three spatial dimensions fundamental? With higher dimensions being purely mathematical abstractions, this question has profound implications for physics. The number of dimensions affects how forces work and how particles behave. In three dimensions, gravity follows inverse square law. Force decreases with square of distance. In different numbers of dimensions, gravity would behave differently. The laws of physics depend on dimensionality. Observationally, we perceive 3 spatial dimensions. We move through space in 3 independent directions. Any object's position is specified by 3 numbers. Any volume is measured in cubic units. This 3-dimensional structure seems fundamental to physical law and our experience of reality. But appearances can be deceiving. Physics has repeatedly revealed hidden aspects of reality. Atoms weren't visible until we developed appropriate tools. Quantum mechanics revealed probabilistic nature beneath classical determinism. Perhaps extra dimensions exist but remain hidden from direct perception. They could be compactified, curled up so small we don't notice them. Or they could be inaccessible to ordinary matter, affecting only gravity or exotic particles. Various theoretical frameworks propose extra dimensions for different reasons. String theory requires extra dimensions for mathematical consistency. Kaluza-Klein theory adds 1 dimension to unify gravity and electromagnetism. Braneworld scenarios suggest we're confined to 3-dimensional surface in higher dimensional space. Each proposal has motivations and predictions. Each suggests reality has more dimensions than we perceive. Understanding whether extra dimensions exist requires both theoretical reasoning and experimental tests. We must determine if physics requires extra dimensions and whether observations can detect them. The journey begins with appreciating what we know. 3 spatial dimensions provide the stage for all observed phenomena. Length, width, and height define the space we navigate. These 3 dimensions are real and familiar, but they might not be the whole story. Hidden dimensions might exist at every point, too small to see, or vast dimensions might extend beyond our reach, inaccessible to ordinary exploration. The question is open. Physics hasn't definitively answered how many dimensions exist. This uncertainty is exciting. It means fundamental aspects of reality remain to be discovered. Understanding dimensions deeply requires examining both what we observe and what theories predict. We'll explore both, building a comprehensive picture of dimensionality in modern physics. Before exploring extra spatial dimensions, we must acknowledge the 4th dimension we definitely inhabit: time. Einstein's relativity unified space and time into 4-dimensional space-time, a profound conceptual revolution. Before relativity, space and time were separate. Space was 3-dimensional stage where events occurred in absolute time. Einstein showed this separation is illusory. Space and time are interconnected, forming 4-dimensional continuum. Time is the 4th dimension, but it's different from spatial dimensions in important ways. Spatial dimensions have a positive signature in space-time metric. Time has negative signature. This mathematical difference reflects physical distinction. You can move freely in space but only forward in time. Time's arrow is one way. Entropy increases. Cause precedes effect. Past is fixed. Future is open. Spatial dimensions have no preferred direction. Left and right, forward and backward are equivalent physically, but time is fundamentally directional. This asymmetry distinguishes time from space despite their unification. In space-time, events are specified by 4 coordinates, 3 spatial and 1 temporal. Your position in 4-dimensional space-time includes when as well as where you are. Space-time diagrams visualize this structure. Vertical axis represents time. Horizontal axis represents space. World lines trace objects' paths through space-time, showing their spatial positions across time. Light cones define causal structure. Events inside your past light cone could have influenced you. Events in your future light cone could be influenced by you. This geometric picture reveals deep truths about causality and relativistic physics. Special relativity's effects emerge from space-time geometry. Time dilation, length contraction, and relativity of simultaneity all follow from 4-dimensional structure. Different observers slice space-time differently into space and time. What's simultaneous for one isn't simultaneous for another. but all observers agree on space-time intervals, the four-dimensional distances between events. This invariant shows that four-dimensional space-time is more fundamental than separate space and time. General relativity extends this picture. Space-time isn't just a passive stage but dynamical entity. Mass and energy curve space-time geometry. This curvature is gravity. Einstein's field equations relate matter-energy to space-time curvature in 4 dimensions. The theory's predictions, from gravitational lensing to black holes to gravitational waves, are confirmed observationally. So 4-dimensional space-time is established fact. Time is genuinely a 4th dimension. But when we ask about extra dimensions beyond 3 spatial ones, we typically mean additional spatial dimensions, not time. The question becomes, are there 5, 6, or more spatial dimensions beyond the 3 we perceive? Is space-time actually 5-dimensional, 6-dimensional, or even higher dimensional? Time as 4th dimension provides precedent. Reality can have more dimensions than immediately apparent. Whether additional spatial dimensions exist beyond these 4 is the question we'll explore. But the existence of time as 4th dimension shows that dimensionality can exceed intuition. Reality has at least 4 dimensions. The question is whether it has more. Extra dimensions, if they exist, are spatial dimensions beyond the 3 we experience, hidden from ordinary perception. The concept is mathematically straightforward. Just as 3 dimensions use 3 coordinates, 4 spatial dimensions use 4 coordinates. In 4 spatial dimensions, objects have length, width, height, and a 4th spatial extent perpendicular to all 3. This 4th direction isn't up, down, left, right, forward, or backward. It's independent of all familiar directions. Visualizing this is nearly impossible for humans. Our brains evolved to navigate 3 dimensions. We can't picture 4 spatial dimensions simultaneously, any more than a 2-dimensional being can picture 3. But we can reason about them mathematically and understand their properties abstractly. Distances in 4 spatial dimensions use generalization of Pythagorean theorem. Distance squared equals sum of squared differences in all 4 coordinates. Not just 3, volumes become hypervolumes, spheres become hyperspheres, cubes become tesseracts or hypercubes. These objects have properties we can calculate even if we can't visualize them. A hypercube has 16 vertices, 32 edges, 24 square faces, and 8 cubic cells. These numbers follow patterns extending from lower dimensions. Each dimension adds new structure. Similarly, 5 spatial dimensions add another perpendicular direction. 6 dimensions add yet another. Mathematics accommodates any number of dimensions. The question is whether nature uses them. If extra dimensions exist, why don't we perceive them? Several possibilities explain this. The most common proposal is compactification. Extra dimensions could be curled up into tiny shapes. Imagine space as 2-dimensional sheet from afar. Up close, each point might be a tiny circle. The circle represents a 3rd dimension too small to notice at large scales. Similarly, our 3-dimensional space might have extra dimensions curled into tiny shapes at each point. These compactified dimensions could be extraordinarily small, perhaps Planck length scale. At such scales, about 10 to the minus 35 meters, quantum gravity effects dominate. Probing these scales directly is impossible with current or foreseeable technology, so extra dimensions could exist at every point in space without being directly observable. Another possibility is that extra dimensions are large but inaccessible to ordinary matter. Perhaps matter is confined to a 3-dimensional surface, a brain, embedded in higher dimensional space. We couldn't move into extra dimensions because fundamental forces constrain us to the brain. But gravity, being space-time curvature, might propagate through all dimensions. This could explain gravity's weakness compared to other forces. It's diluted by spreading through extra dimensions. Both scenarios, compactified dimensions and large inaccessible dimensions are theoretically viable. These theoretical motivations don't prove extra dimensions exist, but suggest they're worth investigating. Extra dimensions represent one of physics' most speculative yet potentially revolutionary ideas. If real, they would fundamentally change our understanding of space, forces, and particles. If absent, their theoretical exploration still teaches us about geometry and physics possibilities. Either way, considering extra dimensions pushes physics toward deeper understanding. The question isn't idle speculation, but serious scientific inquiry with mathematical rigour and experimental consequences. The idea of extra dimensions in physics originated in the 1920s with Kaluza-Klein theory, an elegant but ultimately incomplete attempt to unify forces. In 1919, Theodor Kaluza proposed a remarkable idea to Albert Einstein. What if space-time had not 4 but 5 dimensions, 3 spatial, 1 temporal, and 1 additional spatial dimension? Kaluza showed that Einstein's general relativity in 5 dimensions naturally contained both gravity and electromagnetism. By adding 1 extra dimension, the theory unified the 2 known forces. The extra dimension had to be compactified, curled into a tiny circle at every point in space. The circle's radius would be so small that the dimension remains hidden from direct observation. Einstein was intrigued but initially skeptical. The idea seemed too speculative. But Oscar Klein developed the theory further in 1926, providing quantum mechanical justification. Klein calculated that the extra dimension should be curled up at about Planck length scale. This made the theory more concrete. The extra dimension had a specific, though tiny, size. Kaluza-Klein theory's appeal was its geometric elegance. It unified seemingly different forces through geometry. Electromagnetism emerged from gravitational field components in the extra dimension. Electric charge corresponded to momentum in the 5th dimension. Photons were gravitational waves polarized in the extra dimension. This geometric unification was beautiful. Different forces became aspects of higher dimensional geometry. However, Kaluza-Klein theory had problems. It predicted a new particle, the Kaluza-Klein particle, not observed experimentally. It couldn't incorporate the strong and weak nuclear forces discovered later. And the mechanism for compactifying the extra dimension wasn't explained. It was assumed rather than derived. Despite limitations, Kaluza-Klein theory established crucial precedent. It showed that extra dimensions could play physical role. Not just mathematical abstraction, it demonstrated that unification might require geometry in higher dimensions. It provided framework for thinking about compactified dimensions. These ideas would be revived and extended decades later in string theory. String theory requires not 5 but 10 or 11 dimensions for consistency. Like Kaluza-Klein theory, most dimensions are compactified, curled up small. The compactification geometry determines which particles and forces emerge in low-energy physics. This is Kaluza-Klein mechanism applied more broadly. Extra dimensions geometry dictates observed physics. Modern understanding of extra dimensions owes much to Kaluza and Klein's pioneering work. They showed that extra dimensions aren't just mathematical curiosities, but potential physical reality. The key insight was compactification. Extra dimensions needn't be large and obvious. They could be tiny, hidden at every point, affecting physics without being directly perceived. This resolved apparent contradiction between mathematics allowing many dimensions and observation revealing 3. Both could be true if extra dimensions are compactified. Kaluza-Klein theory also illustrated theoretical physics methodology. Start with mathematical framework. General relativity. Extend it to higher dimensions. Examine what new physics emerges. Look for unification or simplification. Make predictions. Test against observation. This approach characterizes modern efforts to understand extra dimensions. String theory, Braneworld models, and other frameworks follow similar methodology. String theory provides the most compelling modern reason to believe extra dimensions exist. The theory requires them for mathematical consistency. String theory proposes that fundamental constituents of nature aren't point particles, but one-dimensional strings. These strings are extraordinarily small, about Planck length, far below observable scales. Different vibration modes of strings correspond to different particles. An electron is one vibration pattern, a quark another. This unifies all particles into a single framework. Everything is strings vibrating in different ways. String theory also naturally incorporates gravity. One vibration mode corresponds to the graviton. This makes string theory a candidate for quantum gravity, unifying quantum mechanics and general relativity. But string theory has a remarkable requirement. It's mathematically consistent only in specific numbers of dimensions. For superstring theory, the most studied version, space-time must have exactly 10 dimensions, 9 spatial dimensions and 1 time dimension. No more, no fewer. This isn't a choice or assumption. It emerges from requiring quantum mechanical consistency. String theory calculations produce anomalies, mathematical inconsistencies, in wrong numbers of dimensions. But if it does, extra dimensions are real and present at every point in space. You would be right now embedded in 10-dimensional space-time with 6 dimensions curled up microscopically. Every point in your body extends into 6 extra dimensions you can't perceive. This is strange thought, but perfectly consistent mathematically. String theory thus transforms extra dimensions from speculative possibility to theoretical necessity. If string theory is right, the question isn't whether extra dimensions exist, but what shape they have. This motivates experimental searches for extra dimensions and studies of their properties. It also drives theoretical work on compactification geometry and its implications. String theory provides rich framework connecting extra dimensions to particle physics, quantum gravity, and cosmology. Whether nature actually uses this framework remains to be determined, but string theory shows that extra dimensions can be integral to fundamental theory, not mere curiosities. The theory's requirement for exactly 10 dimensions suggests something deep about mathematics and physics. Perhaps certain numbers of dimensions have special properties, making consistent theories possible. Or perhaps our universe exists in 10 dimensions for reasons we don't yet understand. These questions motivate continued research in string theory and alternative approaches. For now, string theory stands as major theoretical motivation for taking extra dimensions seriously. If extra dimensions exist, they must be hidden. Compactification is the mechanism by which large dimensions become effectively invisible. The basic idea is that a dimension can be finite and closed, forming a circle or more complex shape. Imagine a garden hose viewed from far away. It appears one-dimensional, just a line. But up close, each point on the line is actually a tiny circle wrapping around the hose. The hose has 2 dimensions, one large and extended, one small and compactified. An ant on the hose could walk along its length or around its circumference. The circumference direction is a second dimension, but from far away we don't notice it. Similarly, our 3-dimensional space might have extra dimensions compactified at every point. Each point extends into extra dimensions curled into tiny shapes, too small to perceive. The size of these compactified dimensions is crucial. If they're small enough, we can't detect them directly. Current physics probes scales down to about 10 to the minus 19 meters at the Large Hadron Collider. This means compactification geometry essentially determines observed physics. The hierarchy of particle masses, the strengths of forces, perhaps even number of particle generations could reflect geometry. Understanding compactification is therefore key to connecting string theory to observed particle physics. But compactification also makes the theory less predictive. With many possible shapes, many outcomes are possible. This landscape problem challenges string theory's ability to make unique predictions. Compactification isn't unique to string theory. Any theory with extra dimensions must address how they hide. Braneworld models propose different mechanism. Extra dimensions might be large but perpendicular to where we can go. We're confined to three-dimensional brain-like beings on a membrane surface. Extra dimensions extend perpendicular to the brain, but are inaccessible to matter and forces except gravity. This is different hiding mechanism but serves similar purpose, making extra dimensions undetectable in most experiments. Mathematically, compactification involves topology and differential geometry. The compact dimensions form a manifold, a geometric space with particular properties. The manifold's size, shape and symmetries all affect physics in the larger dimensions. Quantum mechanics on compact spaces produces discrete energy levels, like particle in a box. Particles moving in compactified dimensions have quantized momenta, appearing as mass from four-dimensional perspective. These Kaluza-Klein modes are towers of increasingly massive particles, corresponding to motion in extra dimensions. Detecting these modes would be evidence for extra dimensions. Compactification shows how reality can be higher dimensional while appearing lower dimensional. The mechanism is elegant. Dimensions can be finite and small, present everywhere but imperceptible. This resolves apparent contradiction between mathematics allowing many dimensions and experience revealing three. Both are correct at different scales. If extra dimensions exist, how can we detect them? Several experimental signatures might reveal hidden dimensions. The most direct approach is searching for Kaluza-Klein particles at colliders. If extra dimensions exist, particles moving in those dimensions would appear as heavier versions of known particles. These Kaluza-Klein modes would show up as resonances in particle collisions. The Large Hadron Collider has searched for such signatures without finding definitive evidence. This constrains extra dimension size. If they were large enough, Kaluza-Klein modes would have appeared. Current limits suggest compactified dimensions smaller than about 10 to the minus 19 meters. Graviton Kaluza-Klein modes are particularly interesting. Gravity propagates in all dimensions. If extra dimensions exist, gravitons should have excited modes corresponding to extra-dimensional motion. These would couple weakly to ordinary matter but might be detectable in precision experiments. Missing energy in collisions could indicate graviton Kaluza-Klein modes escaping into extra dimensions. Experiments search for events where energy momentum isn't conserved in visible dimensions. This could mean particles or energy escaped into hidden dimensions. So far, no convincing signals have been found, again constraining extra dimension sizes. Gravity provides another probe. Newton's gravitational law holds at large scales, but at very small distances, deviations might indicate extra dimensions. If gravity propagates through more than 3 spatial dimensions, its strength should increase at small distances. Torsion balance experiments test gravitational law at microscopic scales. They compare gravitational attraction between small masses separated by tiny distances. These experiments have tested Newton's law down to about 50 micrometers. No deviations are observed, constraining large extra dimension size. If extra dimensions were larger than micrometers, gravity would behave differently at these scales. But absence of evidence isn't evidence of absence. Extra dimensions could be smaller than current sensitivity, or they might manifest in ways not yet tested. The search continues with improving technology. Future colliders, if built, would probe smaller scales and higher energies. More sensitive gravitational experiments continue pushing limits. Better astrophysical observations refine constraints. The question remains open. Experimental physics hasn't ruled out extra dimensions, but hasn't confirmed them either. This is frontier territory, where theory outpaces experiment, and experiments are catching up. While string theory suggests tiny compactified dimensions, alternative scenarios propose large extra dimensions hidden in different ways. The Braneworld scenario, proposed in late 1990s, revolutionized thinking about extra dimensions. It suggested that extra dimensions might be large, even infinite, yet still undetectable. The key idea is that ordinary matter is confined to a three-dimensional brain embedded in higher dimensional space. We're like beings living on a membrane surface, unable to leave it. The bulk, the higher dimensional space surrounding the brain, is inaccessible to us. Standard model particles and forces are confined to the brain through dynamical mechanisms, but gravity, being space-time curvature, propagates through the entire bulk. This setup explains gravity's weakness. Gravity spreads through extra dimensions, diluting its strength on the brain. Electromagnetic, weak and strong forces are confined to 3 dimensions, remaining strong. Gravity alone feels extra dimensions, making it appear weak by comparison. This addresses the hierarchy problem. Why is gravity 10 to the 32 times weaker than other forces? If extra dimensions are large enough, gravity dilution could explain the hierarchy without fine-tuning. The ADD model, named after Arkani Hamed, Dimopoulos, and Diwali, quantifies this idea. If there are n large extra dimensions of size r, gravity's effective strength depends on r and n. For 2 extra dimensions of about millimeter size, observed gravity weakness is explained. This makes testable prediction. Gravity should deviate from Newton's law at millimeter scales. Experiments test this by measuring gravitational force between small masses at tiny separations. Torsion balance experiments have reached about 50 micrometers, finding no deviations. This constrains large extra dimension scenarios. 2 dimensions must be smaller than micrometers. Large extra dimension scenarios show that hidden dimensions needn't be Planck-sized. They could be macroscopic yet hidden through confinement of matter to lower dimensional subspace. This expands possibility space for extra dimensions dramatically. It also makes them more testable. Large dimensions produce stronger effects, easier to detect. The fact that experiments haven't seen these effects constrains but doesn't eliminate the scenarios. Parameters can be adjusted to keep large dimensions consistent with observations. But as experiments improve, the allowed parameter space shrinks. Eventually, large extra dimension models will either be detected or ruled out within certain parameter ranges. This makes them scientifically productive. They motivate experiments and make falsifiable predictions. Whether nature actually uses large extra dimensions remains unknown. But the theoretical possibility shows that our intuitions about extra dimensions can be misleading. Hidden doesn't necessarily mean small. It could mean perpendicular, inaccessible, or warped. One of the most puzzling features of nature is gravity's extreme weakness compared to other fundamental forces, potentially explained by extra dimensions. The electromagnetic force between 2 protons is about 10 to the 36 times stronger than their gravitational attraction. This enormous discrepancy is called the hierarchy problem. In particle physics, the Planck scale, where gravity becomes strong, is 10 to the 19th giga-electron-volts. The electro-weak scale, where electromagnetic and weak forces unify, is about 100 giga-electron-volts. The ratio between these scales is about 10 to the 17th, an enormous hierarchy. Why is gravity so weak? Or equivalently, why is the Planck scale so large compared to electro-weak scale? Standard model doesn't explain this. The hierarchy must be imposed by fine-tuning parameters. Fine-tuning means adjusting values precisely to get desired outcome. Suggesting deeper explanation is missing. Extra dimensions offer potential explanation. If gravity propagates through extra dimensions while other forces don't, gravity is diluted. Imagine spreading butter over bread. Same amount of butter spread over larger area makes thinner layer. Similarly, gravitational force spreading through extra dimensions becomes weaker in 3 visible dimensions. Mathematically, gravitational force in d dimensions follows inverse law with exponent d minus 1. In 3 dimensions, force goes as 1 over distance squared. In 4 dimensions, it would go as 1 over distance cubed. This faster fall-off with distance means weaker force at any given distance. If we measure gravity's strength in 3 dimensions, but it's actually spreading through more, we underestimate true strength. The fundamental gravitational scale could be much lower than Planck's scale. It could be near electroweak scale, solving hierarchy problem. Extra dimensions provide the volume through which gravity spreads, weakening it to observed level. This is quantitative proposal with specific predictions. The size and number of extra dimensions are related to how much gravity is weakened. For 2 mm sized extra dimensions, fundamental gravity scale could be TeV, electroweak scale. This would mean quantum gravity effects appear at LHC energies, not far above. We'd see microscopic black holes or graviton Kaluza-Klein modes in collisions. So far, LHC hasn't observed these phenomena, constraining the scenario, but the logic remains compelling. Extra dimensions naturally explain hierarchies through geometry. In Randall-Sundrum models, warped geometry generates hierarchy even with small extra dimension. The warping causes exponential suppression of energy scales from one brane to another. We live on the brane where scales are suppressed. Gravity's weakness emerges from geometric warping. This is different mechanism but similar result. Geometry explains hierarchy. Both approaches show extra dimensions aren't just mathematical curiosities, but potential solutions to real physics problems. The hierarchy problem is a serious issue in particle physics. Standard model doesn't explain it. Proposed solutions include supersymmetry, compositeness, and extra dimensions. Each has strengths and challenges. None is confirmed experimentally. Extra dimensions' appeal is geometric elegance. Hierarchy arises from space's structure, not arbitrary parameters. This connects fundamental constants to geometry, echoing Einstein's geometric explanation of gravity. If gravity's weakness does reflect extra dimensions, understanding geometry becomes key to understanding forces. Compactification shape, warping, and dimensional structure would determine force strengths. This would be profound unification. Geometry determines dynamics completely. Whether nature works this way remains unknown. But the possibility motivates both theoretical and experimental work. Theorists study compactification geometry and its implications. Experimentalists search for signatures that would confirm or refute extra dimension scenarios. The hierarchy problem persists as major puzzle. Extra dimensions offer one of most elegant proposed solutions. If extra dimensions exist, what would it mean for us? How would it change our understanding of reality and our place in it? Most immediately, it would mean that every point in space extends beyond what we perceive. Right where you are now, 6 or 7 extra dimensions could be curled up invisibly. Every atom in your body extends into these hidden dimensions. Your particles' properties, their masses and charges, might reflect how they move in extra dimensions. An electron's mass might be its momentum in compactified dimensions, quantized by boundary conditions. Particle families might correspond to different ways of wrapping around extra dimensions topology. This would mean particle physics properties are geometric, determined by extra dimension shape. Understanding particles would require understanding multidimensional geometry. Extra dimensions would also mean space-time is far richer than we imagine. Instead of simple 4-dimensional continuum, space-time would be 10 or 11-dimensional manifold. Most dimensions are tiny, but they're present at every event, every point. This higher dimensional structure would be reality's true nature. 3 dimensions we see would be effective description, approximately valid at large scales. At Planck scale, the full dimensionality would become apparent. Quantum gravity would necessarily be higher dimensional theory. Space-time itself might emerge from deeper structure involving all dimensions. Extra dimensions might also explain why space has 3 large dimensions specifically. Perhaps dynamics of compactification favours 3 large and rest small. Or anthropic selection might explain it. life might require 3 spatial dimensions. Too few dimensions and complexity is limited. Too many and atoms don't bind stably. 3 dimensions might be special for hosting complex structures and observers. If we're confined to a brain, our 3-dimensional existence reflects brain's dimensionality. The bulk could have more dimensions, but we're restricted to lower dimensional subspace. This would mean reality has richer structure we cannot access. Travelling through bulk would require new physics. Ways to leave the brain. Such travel might be forever impossible for matter and energy we comprise, or advanced civilizations might discover how to probe or even access extra dimensions. These possibilities are speculative but follow logically from Braneworld scenarios. Extra dimensions would also affect cosmology. Early universe evolution would involve all dimensions. Compactification would have occurred through cosmological processes. Understanding how dimensions became different sizes is open. Question: why did 3 dimensions expand while others remained small or compactified? This initial condition problem might be explained by dynamics or anthropic reasoning. Either way, cosmic history would be story of dimensional evolution. In far future, extra dimensions might be revealed through technological advances. Experiments at higher energies or smaller distances could detect their signatures, or mathematical physics might prove their necessity indirectly through consistency requirements, even without direct observation. We might become convinced through theoretical arguments. Living in higher dimensions would mean embracing richer geometry as fundamental. It would mean that visible reality is projection or restriction of fuller reality. This is a profound shift in perspective, similar to earlier revolutionary insights. Realizing Earth isn't flat-changed geography. Realizing space-time is curved, changed physics. Realizing dimensions exceed 3 would be another expansion of worldview. It would humble us by showing how much we don't directly perceive, but it would also empower us by revealing deeper structure to understand and perhaps manipulate. For now, living in higher dimensions is hypothesis, not established fact. We conduct our lives in 3 spatial dimensions, whether or not more exist. But contemplating the possibility enriches appreciation of reality's potential depth, and it motivates scientific work to discover whether our universe is truly higher dimensional. String theory's requirement for exactly 10 space-time dimensions is one of its most distinctive features, emerging from mathematical consistency conditions. The theory describes fundamental entities as one-dimensional strings rather than point particles. Strings can be open with endpoints or closed loops. They vibrate in different modes. Each vibration mode corresponds to a different particle. Electrons, quarks, photons all emerge from string vibrations. This provides unification. One fundamental object, many manifestations. String theory also naturally includes gravity. One vibration mode is the graviton. This makes string theory a quantum gravity theory, unifying quantum mechanics and general relativity. But achieving this unification requires specific space-time dimensionality. In quantum field theory, calculations can produce anomalies, mathematical inconsistencies where probability doesn't sum to 1. Anomalies ruin a theory's predictive power. Consistent theories must be anomaly-free. String theory calculations produce anomalies in wrong numbers of dimensions. Only in critical dimension do all anomalies cancel. For bosonic string theory, the earliest version, critical dimension is 26. 25 spatial dimensions plus 1 time dimension. This seems absurdly high and unrealistic. Bosonic strings also have tachyons, faster-than-light particles, making them unphysical. Superstring theory improves this. It incorporates supersymmetry, relating bosons and fermions. Supersymmetry cancels tachyons and reduces critical dimension. For superstrings, space-time must have exactly 10 dimensions, 9 spatial, 1 temporal. This isn't a choice. It emerges inevitably from requiring quantum consistency. The mathematics simply doesn't work in other dimensions. Anomalies appear and ruin the theory. In 10 dimensions, 5 consistent superstring theories exist. Type 1, Type 2a, Type B, and 2 heterotic theories. Each has different properties but all require 10 dimensions. In 1990s, these were unified into M-theory framework. M-theory is more fundamental. Living in 11 dimensions, the 5-string theories are different limits or perspectives on M-theory. The 11th dimension's role in M-theory adds richness to framework. It introduces M-branes, higher dimensional objects beyond just strings. 2-dimensional membranes, 5 branes, and other extended objects appear. These objects play crucial roles in theory's dynamics and dualities. But from low-energy perspective, we see at most 3 spatial dimensions. 6 or 7 extra dimensions must be compactified, hidden from ordinary observation. The compactification process takes 10 or 11-dimensional theory down to effective 4-dimensional theory. Different compactifications yield different effective theories. Different particle spectra and force strengths. The compactification geometry is encoded in Calabi-Yau manifolds, complex 6-dimensional spaces with special properties. These manifolds have intricate topology and geometry. The number of "0" in different dimensions, quantified by topological invariance, determines low-energy physics. Particle generations might correspond to topological cycles in Calabi-Yau space. Force coupling constants might be determined by manifolds' volumes and shapes. This connects abstract geometry to observable physics in detailed way. But there are many Calabi-Yau manifolds, perhaps 10 to the 500th distinct possibilities. This landscape problem means string theory doesn't make unique predictions without knowing compactification. Some see this as weakness, reducing predictivity. Others see it as strength, providing flexibility. Perhaps environmental factors or anthropic selection determines which compactification is realized. Or perhaps dynamics we don't understand yet picks out specific compactification. The requirement for 10 dimensions is both string theory's signature and its challenge. Its signature because it's distinctive, unexpected prediction, emerging from consistency. Its challenge because testing 10-dimensional physics with 3-dimensional experiments is difficult. But the requirement shows that dimensionality connects to fundamental consistency. Perhaps only certain dimensions allow viable quantum theories of gravity and matter. This would make dimensionality not arbitrary but determined by deep mathematical constraints. M-theory introduced an 11th dimension and unified the 5 superstring theories into a more fundamental framework. In 1990s, string theory appeared to have 5 distinct consistent versions: Type 1, Type 2a, Type 2ib, and the 2 heterotic theories all lived in 10 dimensions. But they seemed like separate theories with different properties and spectra. This was puzzling. Why would nature have 5 fundamental theories? Physicists expected a unique fundamental theory, not 5 alternatives. The resolution came through understanding dualities, mathematical equivalences between apparently different theories. T-duality relates theories compactified on large and small radii. A theory on radius r is equivalent to another theory on radius 1 over r. Large and small compactifications are physically identical in dual description. S-duality relates weak coupling in one theory to strong coupling in another. When one theory becomes non-perturbative and difficult to calculate, dual theory becomes weakly coupled and easier. Through these dualities, the 5-string theories were shown to be related. They're different limits of a single underlying structure called M-theory. Edward Witten proposed this unification, showing how dualities connect the theories. M-theory lives in 11 dimensions, 10 spatial and 1 temporal. The 11th dimension distinguishes M-theory from 10-dimensional string theories. When the 11th dimension is compactified on a circle, M-theory reduces to Type 2a string theory. Different compactifications of the 11th dimension yield other string theories. So the 5 theories are manifestations of M theory under different conditions. M theory is more fundamental, but it's also less understood. Unlike string theories, there's no complete formulation of M theory. We understand it only through limits and special cases. In the low energy limit, M theory is described by 11-dimensional supergravity. This is classical theory, the supersymmetric extension of general relativity in 11 dimensions. But full quantum M theory remains elusive. Its complete equations and principles aren't known. The 11th dimension introduces new objects called M-branes. M2 branes are 2-dimensional membranes. M5 branes are 5-dimensional. Strings themselves arise as boundaries of M2 branes, or when M2 branes wrap around cycles. These extended objects create rich tapestry of structures beyond just strings. They interact, form bound states, and create complicated dynamics. Understanding M-brane physics is key to understanding M theory fully. The 11th dimension also affects compactification. M theory can be compactified on 7-dimensional manifolds called G2 manifolds. These have special properties preserving some supersymmetry in resulting 4-dimensional theory. G2 compactifications provide different route from M theory to realistic physics. They complement Calabi-Yau compactifications of string theory. The relationship between 11-dimensional M theory and 10-dimensional strings shows dimensional democracy. Different numbers of dimensions arise from different perspectives on same underlying structure. This suggests dimensionality itself might be emergent or perspective dependent. Perhaps fundamental theory doesn't have fixed dimensionality, but different dimensional descriptions in different regimes. This would make the question context-dependent. Answer might be 10, 11, or even different number depending on what limit or regime we examine. M theory's 11 dimensions expanded the framework beyond original string theory. It showed that even the fixed dimensionality of string theory was limit of something richer. Whether 11 dimensions is ultimate answer, or itself a limit of something deeper, remains unknown. But M theory demonstrated that thinking about dimensions requires sophistication. They're not just given numbers but emerge from deeper mathematical structure. Understanding M theory fully would likely clarify what dimensions are fundamentally. For now, M theory stands as promising but incomplete framework, with 11 dimensions emerging from duality and consistency. The geometry of extra dimensions in string theory is encoded in Calabi-Yau manifolds, beautiful mathematical structures determining observable physics. When 6 extra dimensions compactify, they must form a special type of 6-dimensional space. Not just any 6-dimensional shape works. String theory requires specific geometric properties. The space must be a complex manifold, having complex coordinates with special structure. It must be scalar, having a particular metric compatible with complex structure. Most importantly, it must be Ricci flat, having zero Ricci curvature. These conditions define Calabi-Yau manifolds, named after Eugenio Calabi and Xingtung Yau. Calabi conjectured their existence in 1950s. Yau proved it in 1970s. Their relevance to string theory was recognized in 1980s by Candelas, Horowitz, Strominger, and Witten. Calabi-Yau manifolds preserve supersymmetry when extra dimensions compactify on them. Supersymmetry is symmetry relating bosons and fermions, important for string theory's consistency. Preserving some supersymmetry in 4 dimensions requires special compactification geometry. Calabi-Yau manifolds provide this geometry automatically through their mathematical properties. The simplest Calabi-Yau manifold is the quintic, defined by polynomial equation in 5-dimensional complex space. More complicated Calabi-Yau spaces have intricate topology with many cycles and features. The topology is characterized by Hodge numbers, integers counting different types of cycles. These numbers determine how many particle families appear in low-energy physics. For instance, the number of electron-like particles might equal certain Hodge number. Moduli are parameters describing Calabi-Yau shape, sizes of cycles, complex structure deformations. Changing moduli continuously deforms the geometry without changing topology. These moduli appear as scalar fields in four-dimensional physics. Their values determine force coupling constants and other physical parameters. So Calabi-Yau geometry directly determines observable physics through its mathematical properties. The problem is that many Calabi-Yau manifolds exist. Thousands were known initially. More systematic counting suggests enormous numbers. Current estimates indicate perhaps 10 to the 500th distinct Calabi-Yau manifolds. Each yields different low-energy physics, different particle spectra and force strengths. This creates the landscape problem. String theory appears to allow vast numbers of possibilities. Without principle to select among them, theory doesn't make unique predictions. Some hope dynamics determines the compactification, making one geometry energetically preferred. Others invoke anthropic reasoning, suggesting we observe the rare geometry compatible with life. Still others see landscape as feature, not bug, with environmental variation selecting observed physics, regardless. Calabi-Yau manifolds show how abstract geometry determines physics. The shapes of six-dimensional spaces nobody has seen dictate properties of particles everyone observes. This is profound connection between mathematics and physical reality. It suggests geometry at fundamental level determines everything about nature. Studying Calabi-Yau manifolds is challenging. They're six-dimensional complex spaces, difficult to visualize. Mathematicians use algebraic geometry and differential geometry to characterize them. The mathematics is sophisticated, requiring advanced techniques. But progress continues. New Calabi-Yau spaces are discovered. Their properties are catalogued. Mirror symmetry, a duality between pairs of Calabi-Yau manifolds, has been a powerful tool. It relates difficult calculations in one geometry to easier calculations in mirror geometry. This has applications beyond string theory, advancing pure mathematics. Calabi-Yau manifolds exemplify how theoretical physics drives mathematical development. Physicists' needs motivate mathematicians' research. Mathematics enables physics progress. The interplay enriches both fields. For string theory, Calabi-Yau manifolds are central. They're where extra dimensions hide. Understanding them is understanding how 10 dimensions appear as 4 at low energies. This makes Calabi-Yau geometry essential to connecting string theory with observable universe. Braneworld scenarios propose that we live on a three-dimensional brain embedded in higher dimensional space, offering alternative picture of extra dimensions. The word brain is short for membrane, generalized to any dimensional surface. A zero brain is a point, a one brain is a string, a two brain is a surface, a three brain is three-dimensional volume, potentially our universe. In Braneworld models, ordinary matter is confined to a three brain. Standard model particles can't leave the brain. They're stuck to it through dynamical mechanisms. But gravity, being space-time curvature, propagates through all dimensions. The bulk, the higher dimensional space surrounding the brain, contains only gravity. This setup explains why we perceive three dimensions. We're physically confined to three-dimensional subspace. Extra dimensions exist perpendicular to our brain but are inaccessible. This is a different hiding mechanism than compactification. Dimensions aren't tiny but perpendicular. The ADD model uses this setup to explain gravity's weakness. If bulk has large extra dimensions, gravity spreads through them, diluting on our brain. This makes gravity appear weak without actually being fundamentally weak. The Randall-Sundrum models propose warped brain worlds with distinctive features. RS1 model has two brains separated in a fifth dimension. The geometry is warped, with metric depending on position in fifth dimension. We live on the TeV brain where scales are exponentially suppressed. Gravity is strong on the Planck brain but warped to weakness on our brain. This generates large hierarchy through small geometric warping. RS2 model has single brain in infinite fifth dimension. Despite infinite extra dimension, Four-dimensional gravity emerges on the brain. The warping localizes gravity to the brain region even though extra dimension is infinite. This is remarkable. Infinite extra dimension, yet four-dimensional physics. Braneworld scenarios arose from string theory insights. D-branes are objects where open strings end. They're higher dimensional versions of strings. Our universe might be a D3 brane with standard model particles as open string endpoints. Closed strings, including gravitons, propagate in bulk away from brane. This naturally confines matter while allowing gravity to spread. Braneworld models make testable predictions. They modify gravitational force law at small distances in specific ways. They predict Kaluza-Klein graviton resonances with characteristic patterns. They affect cosmology, particularly early universe expansion rate. Gravitational waves from Braneworld scenarios have distinct signatures. Extrapolarization modes or modified propagation could reveal brane structure. Future gravitational wave observations might detect these signatures. Collider physics could produce black holes or gravitons escaping into bulk. These would appear as missing energy events with particular kinematics. LHC has searched for such signatures without finding them, constraining parameters. Braneworld scenarios also raise cosmological questions. How did brane form? What determines its dimensionality? Are there other branes? Could they collide? The ekpyrotic scenario proposes that brane collisions trigger big bangs. Our universe's beginning might have been collision between branes in higher dimensional space. These ideas are speculative but show how braneworlds connect to cosmology. Philosophically, braneworlds change perspective on reality. We're not inhabiting all of space but confined to lower dimensional subspace. Fuller reality extends perpendicular in directions we cannot access. This is humbling, showing how limited our direct perception might be. But it's also exciting, suggesting richer structure to explore. Braneworld scenarios demonstrate that extra dimensions can hide through confinement, not just compactification. This expands possibility space and connects to string theory's brane dynamics. Whether we actually live on a brane remains unknown, but the models are theoretically rich and experimentally testable. While extra dimensions are compelling, alternative explanations exist for phenomena they aim to explain, and string theory isn't the only game in town. Loop quantum gravity is a major alternative to string theory for quantum gravity. It quantizes spacetime geometry directly without requiring extra dimensions. Space becomes discrete at Planck scale, built from quantum loops called spin networks. This approach stays in 4 spacetime dimensions, working with general relativity's geometry. Loop quantum gravity resolves singularities through quantum effects, not extra dimensions. It makes predictions about Planck-scale physics without invoking hidden dimensions. Whether it fully succeeds as quantum gravity theory remains debated. But it shows extra dimensions aren't necessary for quantum gravity conceptually. For the hierarchy problem, alternatives to extra dimensions exist. Supersymmetry proposes symmetry between bosons and fermions. Each standard model particle has supersymmetric partner with different spin. These partners cancel quantum corrections that would destabilize hierarchy. This stabilizes weak scale without requiring extra dimensions. However, LHC hasn't found supersymmetric particles where expected. Challenging simple versions. Compositeness proposes that particles aren't fundamental but made of smaller constituents. Higgs boson might be composite, like pions made of quarks. This makes weak scale natural as binding energy scale. No extra dimensions are needed, just new strong force at TV scale. Again, experiments haven't confirmed this scenario yet. Technicolor is a related idea where new strong force breaks electroweak symmetry. It avoids fundamental Higgs field through dynamics. This addresses hierarchy without extra dimensions but faces phenomenological challenges. For unifying forces, alternatives to Kaluza-Klein unification exist. Grand unified theories unify forces at high energies without extra dimensions. Strong, weakened electromagnetic forces merge into single force above GUT scale. This uses gauge symmetry in 4 dimensions, not higher dimensional geometry. Guts have successes and challenges but don't require extra dimensions. Some argue extra dimensions are solution-seeking problems. The problems they address might have different solutions or might not be real problems. The hierarchy might be explained anthropically. In multiverse, different regions have different scales. We observe life-compatible values, explaining apparent fine-tuning without dynamics. This doesn't require extra dimensions, just vast landscape of possibilities. Gravity's weakness might not need explanation. It might be fundamental fact. Perhaps hierarchy is coincidence or consequence of other physics we don't understand. Extra dimensions might be unnecessary complication. From observational perspective, extra dimensions remain unconfirmed. All observations are consistent with 3 spatial dimensions. Null results from searches constrain extra dimension scenarios. Some see this as evidence against them, others see it as insufficient sensitivity. The debate continues. Extra dimensions are motivated theoretically but not confirmed empirically. Whether they exist is open question, not settled fact. This scientific uncertainty is healthy. Multiple ideas compete. Evidence will eventually discriminate. For now, extra dimensions are one possibility among several. They're theoretically rich and potentially fundamental, but they're not proven necessary. Alternative frameworks might explain same phenomena without higher dimensions. Or combination of mechanisms might work, some extra dimensions plus some new symmetries. Physics hasn't converged on single answer. Research continues on multiple fronts. This plurality is science working properly, exploring possibilities while awaiting decisive evidence. Extra dimensions might be correct, or alternatives might succeed, or something completely unexpected might emerge. The question quote 3 remains open, inviting continued inquiry from multiple perspectives. One of the deepest questions is why space has exactly 3 large dimensions if more dimensions exist. Why this particular dimensional structure? This question has both dynamical and anthropic aspects, each providing partial answers. Dynamically, we can ask if some physical process naturally produces 3 large dimensions. Perhaps cosmological evolution starts with all dimensions small, and 3 happen to expand. Inflation might preferentially expand certain directions while others remain compactified. But why 3 specifically? What distinguishes these 3 from others? String theory landscape might provide answer. Among vast possibilities, perhaps 3 large dimension solutions are common or stable. Anthropic reasoning offers complementary perspective. Perhaps only 3 large dimensions support complexity and observers. In fewer than 3 dimensions, physics becomes too constrained. 2 spatial dimensions don't allow complex structures. Atoms can't bind properly. In 2 dimensions, gravitational and electromagnetic potentials behave differently. Planetary orbits are unstable. Chemistry wouldn't work as needed for life. Even fundamental particles might not exist in familiar forms. In more than 3 dimensions, stability problems arise. Planetary orbits become unstable in 4 or more spatial dimensions. Atoms might not be stable. Electrons could spiral into nuclei. The inverse square law generalizes differently in higher dimensions, affecting binding. Chemistry and complex structures might be impossible. String theory calculations suggest atoms are unstable in more than 3 spatial dimensions. The delicate balance allowing molecular complexity might require exactly 3. This anthropic argument says we observe 3 dimensions because observers require 3. Universes with different dimensionality exist in the landscape but don't produce observers to notice. Selection bias explains observation. We necessarily find ourselves in life-compatible region. But this doesn't explain why 3-dimensional solutions exist at all, or why they're accessible. Mathematical physics also suggests 3 dimensions might be special. Certain equations have special properties in 3 dimensions not shared by others. Maxwell's equations, for instance, have particular elegance in 3 spatial dimensions. Wave equations behave specially in 3 dimensions with sharp propagation. These mathematical features might reflect deeper structure. Perhaps 3 dimensions emerge from fundamental theory for mathematical reasons. Or perhaps we're noticing patterns, but causation runs differently. The question connects to time having 1 dimension versus 3. Why 1 time and 3 space? Why not 2 of each, or different distribution? Having multiple time dimensions creates causality problems and instabilities. Predictability breaks down with more than 1 time dimension, so 1 time seems necessary. But does that constrain spatial dimensions? Perhaps space-time dimensionality is package deal determined by fundamental consistency. String theory's 10 dimensions might be minimal consistent dimensionality. 3 large space plus 1 time emerges through compactification dynamics or anthropics. Currently, we lack complete understanding of dimensional selection. String theory landscape contains solutions with different numbers of large dimensions. Why nature chose our particular solution from vast possibilities isn't explained dynamically. Anthropic reasoning provides partial answer but doesn't explain mechanism. This remains frontier question. Understanding why 3 large dimensions requires understanding compactification dynamics better. It requires understanding landscape statistics and how solutions are populated. It might require understanding quantum cosmology and how universes are born. Or it might ultimately be anthropic, with us existing where conditions permit. The question, why 3, is profound because it asks why our most basic experience has particular structure. Length, width, height define our existence. Why this specific set? Answering fully would connect dimensionality to fundamental consistency, dynamics, and perhaps necessity of observers. It would complete picture of why reality has its observed structure. For now, 3 large dimensions are given. We experience them and build physics on them. But understanding why they're 3 rather than 2 or 4 would be major advance. It would show dimensionality isn't arbitrary, but determined by deep principles. Extra dimensions have profound implications for cosmology, affecting the early universe, expansion history and ultimate fate. In early universe, all dimensions might have been comparable size. As universe cooled, some dimensions compactified, while others expanded. This dimensional evolution is part of cosmic history. Understanding how it occurred requires understanding compactification dynamics. In string cosmology, the moduli fields describing extra dimension sizes evolve cosmologically. These fields have potential energy depending on their values. The universe seeks minimum of this potential, stabilizing extra dimensions. This moduli stabilization is technical challenge. Extra dimensions must reach small, stable sizes. Various mechanisms are proposed. Fluxes threading compact dimensions, branes wrapping cycles, non-perturbative effects. Each mechanism stabilizes moduli differently with different phenomenological consequences. Stabilization affects inflation and reheating, the universe's earliest dynamics. Extra dimensions modify Friedmann equation governing cosmic expansion. Additional terms appear from higher dimensional gravity. In very early universe, these terms might dominate changing expansion rate. This affects predictions for primordial nucleosynthesis and structure formation. Observations constrain how much extra dimensions could have influenced early cosmology. Cosmic microwave background provides especially stringent constraints. CMB acoustic peaks encode expansion history and physics at recombination. Extra dimension effects would modify peak heights and locations. Current observations are consistent with standard 4-dimensional cosmology. This limits how strongly extra dimensions could have affected early universe. Braneworld cosmology proposes distinctive scenarios. Inflation might occur through brane dynamics, with brane position in extra dimension evolving. The ekpyrotic scenario suggests Big Bang resulted from brane collision. Two branes in higher dimensional space collide, creating hot matter that becomes our universe. This provides alternative to standard inflation with different predictions. Distinguishing between inflation and ekpyrotic scenarios requires precision observations. Their gravitational wave signatures differ. Primordial tensor modes have different amplitudes. Future CMB observations might detect these differences. Dark energy, mysterious component accelerating cosmic expansion, might relate to extra dimensions. Moduli fields from extra dimensions could contribute to dark energy. Their potential energy acts like cosmological constant or evolving quintessence. This connects particle physics of extra dimensions to cosmological dark energy. However, getting right dark energy density is technically challenging. Moduli tend to contribute either too much or too little dark energy. Fine-tuning seems required, recreating similar problem to hierarchy. Some propose the landscape naturally produces small dark energy through anthropic selection. Among vast possibilities, rare solutions with small dark energy allow structure formation. We observe such solutions because large dark energy prevents galaxy formation. This controversial idea uses anthropics to explain otherwise inexplicable fine-tuning. Black holes in higher dimensions behave differently than four-dimensional black holes. Higher dimensional black holes have different horizon geometries and thermodynamic properties. If large extra dimensions exist, black holes produced at colliders would be higher dimensional. They would evaporate differently than four-dimensional black holes. Studying such black holes would probe extra dimensions directly. However, LHC hasn't produced black holes, suggesting extra dimensions are smaller than initially hoped by some scenarios. Cosmological constant problem, why vacuum energy is so small, might involve extra dimensions. Perhaps vacuum energy gravitates only in higher dimensions, not on our brain. This could explain why we don't feel enormous vacuum energy predicted by quantum field theory. The energy exists but curves extra dimensions, not visible space. This self-tuning mechanism is attractive but faces technical challenges. Making it work requires special brain configurations and can create instabilities. Understanding cosmological implications of extra dimensions requires integrating string theory, cosmology, and observations. Progress comes from theoretical calculations and increasingly precise measurements. As observations improve, they either detect extra dimension signatures or constrain them further. Either outcome advances understanding of cosmic history and fundamental structure. Extra dimensions would leave distinctive signatures in particle physics experiments, particularly at high-energy colliders like the Large Hadron Collider. The most direct signature is Kaluza-Klein particle production. When particles move in compactified dimensions, their momentum is quantized. This quantized momentum appears as mass from four-dimensional perspective. For each standard model particle, there's Tower of Kaluza-Klein excitations. These are heavier versions corresponding to motion in extra dimensions. The mass spacing between levels depends on compactification scale. If extra dimensions have size r, mass gaps are approximately 1 over r. For Planck-size dimensions, gaps are huge, 10 to the 19th giga-electron volts. These are far beyond experimental reach. We can't produce such massive particles. But if extra dimensions are larger, gaps are smaller and possibly accessible. For TV-scale extra dimensions, Kaluza-Klein modes could be produced at LHC. They would appear as resonances in collision events. Excited quarks, leptons, and gauge bosons would show up as peaks in invariant mass distributions. Searches for such resonances have found nothing, constraining extra dimension size. Graviton-Kaluza-Klein modes are especially interesting. Gravitons couple weakly to ordinary matter, making them hard to detect. But in collision processes they could be produced and escape into extra dimensions. This creates missing energy signature. Energy and momentum aren't conserved in visible dimensions. Experiments search for events with large missing transverse energy, plus photons or jets. These monojet or monophoton events could indicate graviton production. So far, observations match standard model predictions without extra contribution. This constrains extra dimension scenarios, particularly those with large extra dimensions. Another signature is black hole production. If fundamental Planck scale is low due to large extra dimensions, black hole production becomes possible. When particles collide with energy above effective Planck scale, they could form tiny black holes. These black holes would be higher dimensional, described by higher dimensional general relativity. They'd evaporate nearly instantly through Hawking radiation. The evaporation produces characteristic spherical spray of particles. All particle types would appear with specific thermal distribution. This distinctive signature would clearly indicate black hole production. LHC has searched for such events without finding them. This means fundamental Planck scale isn't as low as large extra dimension scenarios hoped. Either extra dimensions are smaller or fewer than needed to lower Planck scale to LHC energies. Precision measurements also constrain extra dimensions. Virtual Kaluza-Klein particles contribute to processes through quantum loops. They modify scattering amplitudes and decay rates slightly. Precision electroweak measurements constrain these contributions. The Z boson mass, decay width, and branching ratios are sensitive to new physics. Extra dimension effects would show up as deviations from standard model predictions. Current measurements agree with standard model to sub% precision. This constrains extra dimension compactification scales and geometries. Flavor physics provides additional constraints. Kaluza-Klein modes could mediate rare processes forbidden or suppressed in standard model. For instance, they could contribute to kaon mixing or B-Meson decays. Observations of rare processes limit how strongly Kaluza-Klein modes can couple. This constrains compactification geometry's flavor structure. Neutrino physics might reveal extra dimensions. Neutrinos could propagate through bulk if they're not confined to branes. This would modify neutrino oscillations or allow new mixing patterns. Neutrino experiments constrain such possibilities, but haven't definitively ruled them out. Some propose right-handed neutrinos exist in bulk, explaining neutrino masses. This is speculative but shows how extra dimensions might connect to neutrino puzzles. Future colliders would probe higher energies and smaller distance scales. Proposed machines like ILC, FCC or CLIC could access Kaluza-Klein modes beyond LHC reach. They'd have better precision, detecting subtle virtual effects. Discovering extra dimensions at future colliders would revolutionize physics. It would confirm string theory or related frameworks. It would reveal new spatial dimensions and fundamentally change our worldview. Conversely, continued null results would increasingly constrain or rule out classes of extra dimension models. This would guide theory development towards surviving scenarios or alternatives. The interplay between experiment and theory drives progress. Particle physics provides crucial testing ground for extra dimension ideas. Gravity provides another route to detecting extra dimensions through precision measurements at small distances and astrophysical observations. Newton's gravitational law is well tested. At large scales, planetary orbits, satellite trajectories, and galaxy dynamics confirm inverse square law. But at very small distances, tests become difficult and deviations could appear. If extra dimensions are large, gravity would deviate from Newton's law at distances comparable to extra dimension size. In 3 dimensions, gravitational force goes as 1 over distance squared. With n additional dimensions of size r, force follows modified law below distance r. At distances much larger than r, extra dimensions don't matter. Standard inverse square law holds. At distances comparable to or smaller than r, force would strengthen faster than inverse square. Torsion balance experiments test gravitational force between small masses at tiny separations. These experiments are extraordinarily challenging, requiring extreme precision and isolation from disturbances. They place masses near each other and measure force through tiny deflections. Current experiments probe down to about 50 micrometers. No deviations from Newton's law are observed at this scale. This means extra dimensions, if they exist, are smaller than 50 micrometers. For 2 extra dimensions, this implies less than about 30 micrometers. For more extra dimensions, constraints are weaker. 7 extra dimensions could be Planck-sized. Future experiments aim to probe smaller distances with better sensitivity. Reaching micron or submicron scales would test stringent extra dimension scenarios. But below a certain scale, quantum effects and Casimir forces become dominant backgrounds. This sets practical limit on how small distances can be probed. Astrophysical observations provide complementary constraints. If Kaluza-Klein gravitons exist, stars could lose energy by radiating them into bulk. This would affect stellar evolution, changing cooling rates and lifetimes. Observations of stellar properties constrain how much energy loss is allowed. White dwarf cooling, supernova dynamics, and neutron star temperatures all provide limits. These constraints complement laboratory tests. Covering different parameter ranges, gravitational waves offer exciting new probe. LIGO and Virgo detections confirm gravitational waves exist as general relativity predicts. Extra dimensions would modify gravitational wave propagation. Waves could have additional polarization modes beyond general relativity's 2 polarizations. Or waves could disperse, with different frequencies travelling at different speeds. Or waves could be absorbed or scatter into extra dimensions, weakening signals. Current detections show no significant deviations from general relativity. This constrains extra dimension effects on gravitational waves. Future detectors with better sensitivity will test more precisely. LISA, the space-based detector, will observe different frequency range. It might detect effects invisible to ground-based detectors. Pulsar timing arrays, using millisecond pulses as galaxy-scale detector, probe even lower frequencies. Each frequency range tests different aspects of gravity and potential extra dimensions. Gravitational lensing could also reveal extra dimensions. Light bending by mass depends on gravitational field strength. Extra dimensions would modify lensing in specific ways. Precision lensing measurements constrain deviations from general relativity predictions. Cosmological observations of structure growth provide large-scale gravity tests. How quickly galaxies cluster depends on gravitational law. Extra dimensions would modify growth rate in characteristic ways. Observations of large-scale structure constrain such modifications. Together, these gravitational tests span enormous range of scales, from microns in laboratory to cosmological scales across universe. All agree with 4-dimensional general relativity within uncertainties. This either means extra dimensions are very small or don't significantly affect gravity, or it means we're testing within 4-dimensional regime where extra dimensions are hidden. Continued improvements in gravitational measurements will probe deeper. Eventually, either extra dimensions will be detected through gravitational effects or stringently ruled out in accessible parameter ranges. Gravity's universality makes it a powerful probe of fundamental space-time structure. Extra dimensions raise profound philosophical questions about reality, perception, and the nature of space itself. The most basic question is ontological. Do extra dimensions exist, or are they mathematical artifacts? Scientific realism holds that successful theories describe reality, even unobservable aspects. If string theory succeeds and requires 10 dimensions, realists would say 10 dimensions are real. But instrumentalists might argue dimensions are just useful mathematical structures, not claims about reality. This debate parallels historical discussions about atoms, electromagnetic fields, and other theoretical entities. Eventually, accumulating evidence convinces most scientists of theoretical entities' reality. Extra dimensions might follow similar trajectory if evidence accumulates. Or they might remain forever unobservable, raising questions about scientific status. Can we claim something exists if it's in principle unobservable? Philosophy of science grapples with such questions without definitive answers. Extra dimensions challenge our notion of space. Is space fundamental, with dimensionality being intrinsic property, or is space emergent from deeper structure, with dimensions being effective description? Some approaches to quantum gravity suggest space-time itself emerges from more fundamental entities. Dimensions might not be fundamental, but arise in certain regimes. This would make the question context-dependent. The answer might differ at different scales or in different descriptions. Extra dimensions also raise epistemological questions about limits of knowledge. If dimensions are hidden, can we ever know them with certainty? We might infer them indirectly through effects, but direct confirmation could be impossible. This is a general issue in science. Much of reality is known only indirectly. We've never seen atoms directly, yet we're confident they exist. Extra dimensions might be known similarly, inferred with high confidence but never directly perceived. The relationship between mathematics and physical reality becomes crucial. Why does mathematics describe nature so well? Eugene Wigner called this quote 6. If extra dimensions are needed for mathematical consistency, should we believe they're real? Or might consistent mathematics describe non-existent possibilities? Different philosophical positions give different answers. Platonism sees mathematical structures as real. If theory requires 10 dimensions, they exist. Nominalism sees mathematics as human construct describing nature, but not claiming independent existence. Extra dimensions test these philosophical positions. Anthropic reasoning raises its own philosophical issues. If we explain 3 large dimensions through observer requirements, is this science or philosophy? Some philosophers object to anthropic arguments as untestable and unfalsifiable. Others defend them as legitimate reasoning given observational selection effects. The debate continues about anthropic principles' scientific status. Extra dimensions also affect how we think about perception and reality. We perceive 3 spatial dimensions directly. This shapes our intuitions. Learning reality might have more dimensions would be epistemic expansion. It would show direct perception is limited, that reality exceeds intuitive grasp. This has happened repeatedly in science's history. Earth seems flat but is round. Stars seem fixed but move. Time seems absolute but is relative. Each discovery expanded understanding beyond immediate perception. Extra dimensions would be another such expansion. Philosophically, extra dimensions connect questions about fundamentality. Are dimensions fundamental or derived? Is dimensionality necessary or contingent? Could reality have had different dimensionality, or is current dimensionality necessary? String theory suggests certain dimensionalities are special, perhaps necessary for consistency. This would make dimensionality not arbitrary, but determined by deep logic. Understanding why reality has particular structure would be philosophical and scientific achievement. For now, extra dimensions remain possibility, requiring philosophical and scientific consideration. They challenge assumptions, expand possibilities, and deepen questions about reality's nature. Whether they exist is ultimately an empirical question, but contemplating them enriches both philosophy and physics. After exploring extra dimensions from many angles, it's important to clarify what we know with confidence versus what remains uncertain or speculative. We know with certainty that 3 spatial dimensions are macroscopic and directly observable. We navigate through space in 3 perpendicular directions. This is established fact. We know time is a 4th dimension, united with space in 4-dimensional space-time. Einstein's relativity is confirmed through countless observations and experiments. 4-dimensional space-time is real and fundamental to our best physics. We know mathematics allows any number of dimensions without contradiction. Higher dimensional geometry is well defined. We can calculate in any dimensionality. This mathematical freedom doesn't prove extra dimensions exist, but shows they're logically possible. We know string theory requires 10 space-time dimensions for mathematical. Consistency. This is proven fact within string theory's framework, where the string theory describes nature as separate question, but its dimensional requirement is certain. We know compactification can hide dimensions. The garden hose example shows how dimensions can be present yet unnoticed. This provides mechanism for extra dimensions to exist without being obvious. We know precision experiments haven't detected extra dimensions yet. Particle colliders, gravity tests, and astronomical observations find no evidence. This constrains extra dimension properties but doesn't prove they're absent. What remains uncertain is whether extra dimensions actually exist in our universe. String theory's requirement doesn't prove our universe is string theoretic. The theory could be mathematically beautiful but physically wrong. We don't know extra dimension size if they exist. They could be Planck scale, truly microscopic, or large but hidden through Braneworld dynamics. Current experiments constrain possibilities but don't determine size. We don't know extra dimensions shape if they exist. The Calabi-Yau landscape offers vast possibilities. Without knowing which compactification nature chose, predictions are limited. We don't know if large extra dimensions or warped dimensions exist. These scenarios make predictions but aren't confirmed experimentally. We don't know if gravity's weakness relates to extra dimensions. It could be explained by extra dimensions or by supersymmetry or by something else, or might not need explanation. We don't know why space has 3 large dimensions. This could be dynamical outcome, anthropic selection, or perhaps just brute fact. These unknowns are research frontiers. They motivate experiments and theoretical work. What we know provides foundation. 4-dimensional space-time is established. What we don't know creates opportunity for discovery. The balance between knowledge and uncertainty defines scientific progress. We're not completely ignorant but haven't solved all problems. This is healthy state for science. Understanding much while acknowledging much remains unknown. As experiments improve and theories develop, some uncertainties will resolve. We might detect extra dimensions or definitively rule out accessible scenarios. Either outcome advances understanding. For now, honesty requires acknowledging both what's established and what's speculative. Extra dimensions are well-motivated theoretical possibility. They emerge naturally in string theory and address real physics problems. But they're not observationally confirmed facts. This distinction is important for scientific integrity and public understanding. We should communicate excitement about possibilities while acknowledging uncertainties. The question, quote 7, remains open. 4 is certain minimum. Whether more exist is unknown. Extra dimension research continues actively across theoretical physics, experimental physics, and observational cosmology, with several exciting frontiers. Theoretically, string theory research explores compactification geometry and dynamics. Understanding how to stabilize extra dimensions remains active area. New mechanisms for moduli stabilization are proposed and analyzed. The landscape is being explored systematically. Which solutions are generic? Which are special? String cosmology develops early universe scenarios involving extra dimensions. How did compactification occur? Can it be explained dynamically? These questions drive theoretical research. M-theory remains incompletely understood. Formulating it fully is major goal. Understanding the 11th dimension's role more deeply would clarify the framework. Progress comes through studying special cases, dualities, and limits. Gauge gravity duality, ADS-CFT correspondence provides powerful tool. It relates gravitational theories in extra dimensions to quantum field theories without gravity in fewer dimensions. This duality allows calculating difficult problems in one description using easier calculations in dual description. Insights from ADS/CFT inform understanding of quantum gravity in extra dimensions. Applications extend beyond string theory to condensed matter physics and other areas. Experimentally, the Large Hadron Collider continues searching for extra-dimension signatures. Run 3 at higher energies might reveal what earlier runs missed. High luminosity LHC will collect more data, probing rare processes. If Kaluza-Klein modes or microscopic black holes exist near LHC's energy reach, they might appear. Gravitational experiments continue improving sensitivity. Next-generation torsion balances probe smaller distances. These experiments push toward micron and sub-micron scales. Any deviation from Newton's law would be revolutionary discovery. Gravitational wave astronomy is maturing rapidly. LIGO and Virgo detections accumulate. Each observation tests general relativity. Extra-dimension effects would show up as deviations from predictions. LISA, launching in 2030, will open new frequency window. LISA might detect signatures invisible to ground-based detectors. Pulsar timing arrays are becoming sensitive enough to detect gravitational waves. They probe very low frequencies relevant to supermassive black hole mergers. This frequency range might reveal different extra-dimension effects. Cosmological observations provide complementary information. Cosmic microwave background measurements continue improving precision. Planck satellite data is being analysed thoroughly. Future missions are planned. These could detect extra-dimension effects on early universe evolution. Large-scale structure surveys map galaxy distribution precisely. Dark Energy Survey, DESI, and future surveys provide enormous data sets. Structure growth depends on gravitational law. Deviations could indicate extra dimensions. Dark energy missions like Euclid and Roman Space Telescope will constrain cosmic acceleration. If dark energy relates to extra dimension moduli, these observations constrain the connection. Theoretical phenomenology connects formal theory to observations. Researchers calculate detailed predictions for different extra dimension scenarios. These predictions guide experimental searches and interpretation. The interplay between theory and experiment drives progress. Theorists propose scenarios. Experimentalists test them. Results constrain or suggest new theories. This iteration is science working as intended. Interdisciplinary connections enrich research. Condensed matter systems can simulate higher dimensions through internal degrees of freedom. This allows experimental exploration of higher dimensional physics in accessible systems. Quantum information theory provides tools for understanding dimensionality and entanglement. Computer science and machine learning aid in exploring string landscape. The diversity of approaches increases chances of breakthrough. Progress might come from unexpected directions. A chance observation, a new mathematical technique, or insight from different field could crack open mysteries. The current state is active investigation across multiple fronts. No consensus has emerged. Extra dimensions remain possible but unconfirmed. This uncertainty drives continued research. The question is important enough to warrant sustained effort. Looking forward, what might future research reveal about extra dimensions, and how might we finally answer whether they exist? Future particle colliders offer most direct detection possibility. Proposed machines like International Linear Collider would collide electrons and positrons with high precision. This complements LHC's proton collisions, accessing different physics. ILC might detect subtle extra-dimension effects through precision measurements. Future Circular Collider, if built, would reach even higher energies. It could probe smaller distance scales where extra dimensions might manifest. These facilities require enormous investment and international cooperation. Decisions about which machines to build will shape particle physics for decades, if constructed. They could definitively detect or rule out many extra dimension scenarios. Gravitational wave astronomy will mature dramatically. LISA will operate continuously in space, detecting countless sources. Population statistics might reveal extra dimension effects invisible in individual events. Third-generation ground-based detectors are being planned. Einstein Telescope and Cosmic Explorer would have 10 times better sensitivity than current detectors. They detect gravitational waves throughout observable universe. Extra dimension signatures would be easier to identify with such sensitivity. Quantum gravity experiments might probe Planck scale indirectly. Entanglement experiments, quantum computers, and tabletop quantum gravity tests are developing. These might detect signatures of Planck scale physics, including extra dimensions. Cosmological observations will continue improving. Next-generation CMB experiments might detect primordial gravitational waves. These encode information about extremely early universe, when extra dimensions were important. Large-scale structure surveys will map billions of galaxies. Precision constraints on structure growth could reveal extra dimension effects. Dark energy measurements will clarify whether it relates to extra dimension moduli. Astrophysical observations might provide unexpected evidence. Exotic phenomena like fast radio bursts or ultra-high energy cosmic rays might trace to extra dimensions. Astronomical surveys continue finding surprising objects. Some might reveal new physics. Theoretical advances could make predictions more specific. Understanding string landscape better might identify which solutions are likely. This would sharpen predictions even without new experimental data. Developments in quantum gravity might clarify whether extra dimensions are necessary. If complete quantum gravity theory emerges, its dimensional requirements would be definitive. Mathematical advances might prove theorems about dimensionality. Perhaps only certain dimensions allow consistent quantum gravity. This would make question purely theoretical, answerable through math alone. Computational power enables new approaches. Machine learning might find patterns in string landscape invisible to human analysis. Numerical simulations of early universe could show how dimensions evolved. These tools complement analytical methods, exploring possibilities systematically. The timeline is uncertain. Breakthroughs could come soon or take decades. History shows that fundamental questions sometimes resolve quickly when right idea or observation appears. Other times they persist for generations before yielding. Extra dimensions might be answered soon if clear signature appears. Or they might remain ambiguous for a long time if they're beyond experimental reach. Patience and persistence are required. Fundamental questions deserve sustained effort. The prospects are genuinely exciting. Multiple approaches converge. Theory is developing. Experiments are improving. Observations are accumulating. This combination maximizes chances of eventual breakthrough. Whether extra dimensions exist will likely be determined within coming decades. Either they'll be detected, or experimental constraints will become so stringent that they're effectively ruled out in accessible ranges. Either outcome would be major advance in understanding reality's structure. The future of dimensionality research is bright, full of possibility for discovery. As we approach the end of our exploration, perhaps the most important insight is learning to live comfortably with unanswered questions about dimensions. Science doesn't always provide immediate answers. Some questions take generations to resolve. The question quote 8 might be such a question. We may not know the answer in our lifetimes. Future generations might discover it. This is acceptable. Uncertainty is part of scientific endeavour. We work with what we know, while acknowledging what remains unknown. 3 spatial dimensions are certain. Time as 4th dimension is established. Beyond that, uncertainty. Extra dimensions are possible but unconfirmed. Living with this uncertainty means embracing both knowledge and mystery. We understand vast amounts about 3-dimensional space and 4-dimensional space-time. This understanding enables technology, explains observations, and satisfies intellectually. But mystery remains about whether reality extends further. This mystery is valuable. It drives research, inspires curiosity, and keeps science dynamic. If everything were known, science would stagnate. Mysteries provide direction. The question of extra dimensions is a well-posed scientific question. It's not vague philosophy, but precise inquiry with potential empirical answers. Theories make predictions, Experiments test them. This is science functioning properly. That we don't yet have answer doesn't diminish the value of asking. For non-scientists, extra dimensions offer window into frontier physics. They show how theoretical physicists think about space's nature. They demonstrate interplay between mathematics, theory, and experiment. Understanding the question, even without knowing the answer, deepens appreciation for science. Extra dimensions also show how reality might exceed our perception. We directly experience 3 spatial dimensions. Evolution didn't equip us for more, yet mathematically and possibly physically, more dimensions might exist. This expands imagination beyond everyday experience. It suggests humility about assuming we perceive all of reality. Much might operate beyond our direct awareness. This perspective is valuable philosophically and scientifically. For physics students and researchers, extra dimensions provide rich area for contribution. Many problems remain unsolved. Much territory remains unexplored. A student today might make breakthrough tomorrow that reveals extra dimensions. Or they might help rule them out definitively, which is equally valuable. Either way, the work contributes to understanding reality's structure. Living with the question also means being open to surprises. Reality might be stranger than any current theory imagines. Extra dimensions might exist but in unexpected form. Or something completely different might explain phenomena attributed to extra dimensions. Scientific progress often comes from unexpected directions. Maintaining openness while rigorously testing ideas is delicate balance. We need both skepticism and willingness to consider radical possibilities. Extra dimensions exemplify this balance. They're radical yet rigorously formulated. They deserve serious consideration without premature acceptance. The question persists because it matters. Dimensionality is fundamental property. Knowing how many dimensions exist shapes understanding of space, forces, and particles. It's not peripheral detail, but central feature of reality. Eventually, answer will likely emerge. Science tends to resolve clear questions given time. Whether through dramatic detection or accumulating null results, the question will narrow. For now, we live with uncertainty, pursuing understanding patiently. This is mature scientific stance, confident in what we know, honest about what we don't. Extra dimensions remind us that profound mysteries remain. Space itself, most basic aspect of physical existence, might harbour hidden structure. This is humbling and exciting, showing how much we have yet to learn. As we conclude our exploration, let's reflect on what dimensions are fundamentally and what they reveal about reality's nature. Dimensions are independent directions of extent or degrees of freedom in space. They're basic framework within which physical processes occur. 3 dimensions we experience provide stage for all observed phenomena, but dimensions might be more than just background. They might be dynamical. In general relativity, space-time itself is dynamical entity. It curves, expands, and responds to matter. Dimensions aren't fixed background but participate in physics. Extra dimensions, if they exist, would extend this dynamical character. Their sizes and shapes would evolve. They'd interact with matter and forces. This makes dimensions active participants in physics, not passive containers. Understanding dimensions means understanding structure of reality itself. Are dimensions fundamental or emergent? Do they exist independently of matter, or does dimensionality emerge from deeper structure? Some quantum gravity approaches suggest space-time is emergent. More fundamental description might not use dimensions at all. Dimensions would be effective concept applicable at large scales. This would mean asking, quote, 9 is like asking, quote, 10, the answer. Depends on what scale and description you're using. At fundamental level, different description might apply. These possibilities show dimensionality connects to deepest questions about reality. What is space? Is it fundamental substance or relational structure? Does space exist independently or only through objects' relationships? Extra dimensions intensify these ancient questions. If dimensions can hide, be compactified, or be inaccessible, their ontological status becomes puzzling. Are hidden dimensions as real as visible ones? This returns to philosophical questions about reality and observation. Pragmatically, dimensions structure all of physics. Field theories depend on dimensionality. Different dimensions give different physics. Particle physics, condensed matter, cosmology, all use dimensional analysis. Understanding how many dimensions exist would constrain possible theories. It would determine which physics is accessible and which is excluded. This makes dimensionality questions central to theoretical physics foundation. Extra dimensions also illustrate science's reach. We investigate aspects of reality far beyond direct perception. Through mathematics and reasoning, we probe what we cannot see. This is science's power, extending understanding beyond immediate experience. Whether extra dimensions exist is ultimately an empirical question, but contemplating them enriches both physics and philosophy. They force precision about what we mean by space and dimension. They connect to unification, quantum gravity, and fundamental forces. They provide test case for scientific methodology at its frontiers. For you, the listener settling into rest, extra dimensions are distant abstraction. They don't affect daily life whether they exist or not, but they're part of understanding reality's deep structure. Knowing that such questions are being pursued is itself meaningful. Human curiosity extends to fundamental questions about existence. How many dimensions does reality have? The question is profound. The answer, when found, will reshape our understanding of everything. Until then, we continue exploring, measuring, calculating, and theorizing. The journey itself is valuable. Understanding deepens incrementally. Each experiment, each calculation, each theoretical insight contributes. Slowly, the picture clarifies. Either extra dimensions will be revealed or ruled out. Either outcome advances knowledge significantly. Dimensions define the arena of existence. Understanding them is understanding reality's framework. We live in at least 4 dimensions with certainty. Whether we live in 10, 11, or some other number remains to be discovered. The quest continues, driven by curiosity about fundamental structure. This is science at its best. Rigorous inquiry into nature's deepest aspects. Extra dimensions remind us that reality might be far richer than appearances suggest. Hidden structures might exist at every point, shaping everything while remaining invisible. This possibility is both humbling and inspiring. It shows how much we have yet to learn about the cosmos we inhabit. Thank you for journeying with me through dimensions, this exploration of space's structure, and whether reality extends beyond what we can see. I hope you found peace in understanding that the 3 spatial dimensions we navigate might be just the beginning, that hidden dimensions could be curled up at every point, and that reality's true structure might be far richer than everyday experience reveals. How many dimensions do we really live in? We know with certainty 4. 3 spatial dimensions we move through, and time as the 4th, united in space-time. Beyond that, uncertainty. String theory requires 10 dimensions total for mathematical consistency. M-theory adds an 11th. Extra dimensions might be compactified at Planck scale, too small to detect directly, or they might be large but perpendicular, inaccessible to ordinary matter. Braneworld scenarios suggest we're confined to 3-dimensional surface in higher dimensional space. Each possibility makes predictions we're learning to test. Wherever you are now, I hope you're ready for deep rest. Your breathing has found its gentle rhythm. Your mind has released the day's concerns. The dimensional mysteries we've explored perhaps help you feel both grounded in familiar 3-dimensional space and expanded by possibility of hidden dimensions everywhere. Sleep well tonight, knowing that every point in space might extend into dimensions we cannot perceive, that particles' properties might reflect geometry of hidden dimensions, that gravity might spread through extra dimensions explaining its weakness, that reality's true structure might be 10 or 11-dimensional with most dimensions curled microscopically small. Dream peacefully of Calabi-Yau manifolds shaping physics, of brain worlds confining us to lower dimensional surfaces, of extra dimensions waiting to be discovered. Dream of compactification, hiding dimensions at every point, of Kaluza-Klein particles emerging from motion in hidden directions, of string vibrations in 10 dimensions creating all particles and forces. Dream of experiments probing smaller distances, of gravitational wave observations testing extra dimensions, of future colliders possibly detecting signatures of hidden geometry. Good night. May your sleep be undisturbed and restorative. May tomorrow find you refreshed and renewed. And may you carry forward appreciation for how mysterious space truly is, for possibilities beyond ordinary perception, and for ongoing quest to understand reality's dimensional structure. How many dimensions do we really live in? At least 4, possibly 10 or 11, maybe more in ways we haven't imagined. The question remains open, inviting continued exploration through mathematics, experiment, and observation. Space extends in 3 directions we see and perhaps in 6 or 7 directions we don't. Every point might be portal to hidden geometry. Reality might be richer, stranger, and more wonderful than 3 dimensions suggest. Good night.